When you step outside on a clear morning and look up, the sun appears remarkably steady, dependable, and serene. It rises in the east, warms our world, and sets in the west, providing the exact energy that allows life on Earth to flourish. Yet this peaceful golden facade is an illusion. Beneath its dazzling surface, our star is a churning, violent nuclear furnace containing over 300,000 times the mass of Earth, writhing with incomprehensible magnetic forces. And every 11 years, this giant engine undergoes a dramatic transformation, building from quiet stability into a wild tempest of solar flares, magnetic eruptions, and dark sunspots, before resetting all over again. Right now, in 2026, we are living through the absolute crescendo of this cosmic rhythm. Solar cycle 25 is reaching its peak, a phase known as solar maximum. But why is this peak occurring right now? Why did earlier forecasts from leading space agencies predict a much quieter cycle, only for the sun to shatter those expectations? And in an era where human civilization depends entirely on delicate orbital satellites, interconnected power grids, and global navigation systems, what does this heightened solar peak actually mean for our everyday lives on Earth? To understand why the sun behaves this way, we have to look inside its boiling interior. The sun is not a solid sphere like Earth or Mars. It is a gargantuan ball of plasma, an electrically conductive state of matter where intense heat strips atoms of their electrons, creating a turbulent sea of free-flowing charged particles. Because the sun is fluid, it does not rotate as a single rigid body. At the solar equator, the plasma spins rapidly, completing a full rotation in about 25 Earth days. Near the poles, however, the rotation slows down significantly, taking nearly 35 days to complete a single turn. This difference in rotational speed is known as differential rotation, and it is the master clockwork of solar activity. The sun possesses an enormous internal magnetic field generated by the movement of its conductive plasma, a process known as the solar dynamo. In the early stages of a solar cycle, these magnetic field lines run smoothly and neatly from pole to pole, stretching vertically across the sun. But as the equator spins faster than the poles, it drags these magnetic field lines forward, wrapping them tightly around the sun like rubber bands wound around a spinning ball. Year after year, this differential rotation stretches, twists, and shears the magnetic lines of force. Deep within the convection zone, boiling columns of hot plasma rise toward the surface while cooler plasma sinks, further tangling the magnetic flux ropes into dense knots. Eventually, these magnetic concentrations become so intense and buoyant that they punch upward through the photosphere, the visible surface of the sun. Where these powerful magnetic loops break through the surface, they act like giant magnetic brakes, inhibiting the upward flow of heat from the solar interior. This creates localized patches that are roughly 2,000 degrees cooler than the surrounding 6,000-degree surface. Because they are cooler and emit less light, they appear as dark blemishes against the brilliant solar disk. These are sunspots, the primary visual markers of solar activity. Humanity has observed these dark markings for thousands of years, but it was in 1843 AD that the German astronomer Samuel Heinrich Schwabe recognized a clear, repeating pattern. After 17 years of meticulous daily observations, Schwabe realized that the number of sunspots waxes and wanes in a roughly 11-year cycle. Since official scientific record-keeping began in 1755 AD, astronomers have numbered every cycle, making our current phase solar cycle 25. Yet the 11-year sunspot cycle is only half of a larger cosmic story. In 1908 AD, American astronomer George Larry Hale discovered that sunspots possess intense magnetic fields, and that the sun's global magnetic polarity behaves in a fascinating way. During every solar maximum, as magnetic turbulence peaks, the sun's global magnetic field weakens to near zero and completely flips. The magnetic North Pole becomes the South Pole, and the South Pole becomes the North Pole. It takes two 11-year cycles, or approximately 22 years, for the sun's magnetic poles to complete a full cycle and return to their original orientation. This 22-year rhythm is known as the Hale cycle. This brings us to the central mystery. Why is solar cycle 25 peaking right now in 2026? When this cycle officially began in late 2019 AD at the previous solar minimum, an international panel of solar physicists issued a conservative forecast. Based on traditional statistical models and the relatively weak behavior of solar cycle 24, they predicted that cycle 25 would be mild and slow to build, with a modest peak arriving later around 2025 AD or 2026 AD. However, the Sun quickly proved that our predictive models were incomplete. Almost immediately after the cycle began, sunspot numbers began outpacing official projections month after month. Powerful sunspot groups emerged across both hemispheres, unleashing intense solar flares far earlier and more frequently than anticipated. Scientists realized that the Sun was entering a much more vigorous cycle than standard models had envisioned. A major breakthrough in explaining this surge came from solar physicists studying what are known as solar terminators. Deep inside the Sun, giant toroidal magnetic bands of opposing polarity migrate from mid-latitudes toward the equator over long timescales. When the magnetic bands from the previous cycle finally meet at the equator, they suddenly annihilate each other in a rapid event called a terminator. This magnetic cancellation abruptly unleashes the pent-up magnetic flux of the new cycle, causing activity to surge rapidly upward. Heliosismology, the science of studying acoustic sound waves bouncing through the Sun's interior, confirmed that solar cycle 25 had a remarkably strong magnetic foundation. Instead of a narrow, sharp spike, the solar maximum is manifesting as a broad, multi-peaked plateau spanning from late 2024 AD through 2026 AD. In 2026, we are experiencing the final, most unstable phase of this peak, where the Sun's twisted magnetic field lines reach maximum tension just as the global magnetic flip takes place. When the Sun is at this stage of peak magnetic chaos, it unleashes staggering amounts of energy into the solar system. The primary drivers of space weather come in three distinct varieties, each traveling at different speeds and posing different challenges for Earth. The first are solar flares, which occur when tangled magnetic loops suddenly snap and reconnect in an explosive process known as magnetic reconnection. In a fraction of a second, magnetic energy is converted into intense bursts of electromagnetic radiation, from radio waves to energetic X-rays and gamma rays. Traveling at the speed of light, this radiation reaches Earth in just over 8 minutes, ionizing the upper atmosphere and instantly causing high-frequency radio blackouts across the sunlit side of the planet. The second phenomenon consists of solar energetic particle events. These are streams of protons and atomic nuclei accelerated to near-relativistic speeds by the shock waves of flares and eruptions. Arriving in anywhere from 20 minutes to a few hours, these high-energy particles penetrate deep into the polar atmosphere and flood near-Earth space with ionizing radiation, posing severe health hazards to astronauts and degrading solar panels and microelectronics on satellites. The third, and by far the most powerful event, is a coronal mass ejection, or CME. A CME is a colossal bubble of magnetized plasma, containing billions of tons of solar material hurled into interplanetary space at millions of miles per hour. Taking anywhere from 15 to 72 hours to reach Earth, a coronal mass ejection acts like a giant magnetic battering ram smashing into our planet's invisible defenses. Fortunately for all life on the surface, Earth is not defenseless. Our planet possesses its own robust magnetic shield, the magnetosphere, generated by the churning molten iron core deep within our interior. The magnetosphere extends tens of thousands of miles into space, deflecting the vast majority of the lethal solar wind around our planet in a continuous bow shock. However, when a powerful coronal mass ejection collides with the magnetosphere, the outcome depends heavily on the orientation of the solar magnetic field. If the magnetic field carried by the CME points southward, in direct opposition to Earth's northward-pointing magnetic field, the two systems lock together through magnetic reconnection. This opens a doorway that allows immense quantities of solar energy and charged particles to pour directly into Earth's near-space environment, triggering a geomagnetic storm. The most breathtaking and visible consequence of a geomagnetic storm is the aurora, commonly known as the northern and southern lights. As solar particles are funneled along Earth's magnetic field lines toward the polar regions, they plunge into the upper atmosphere and collide with atmospheric gases. When these energetic particles strike oxygen atoms around 60 to 100 miles high, they emit the familiar, ethereal, emerald green glow. Collisions with higher altitude oxygen produce rare crimson-red auroras, while interactions with nitrogen create vibrant ribbons of purple and magenta. During the 2026 solar maximum, these auroral ovals expand dramatically toward the equator, painting night skies across latitudes that almost never witness them. Yet behind this celestial beauty lies an invisible and severe technological vulnerability. Modern civilization is built upon a delicate web of electrical and digital infrastructure that did not exist during most of human history. When geomagnetic storms distort Earth's magnetic field, they induce electrical currents throughout the atmosphere, oceans, and upper crust of the Earth. These are known as geomagnetically induced currents, or GICs. Because these induced currents operate at near-direct current frequencies, they can enter long electrical conductors on the ground, such as high-voltage transmission lines, pipelines, and railway tracks. When geomagnetically induced currents enter giant power transformers, they cause the transformer cores to magnetically saturate. This leads to severe overheating, harmonic distortion, tripping of circuit breakers, and, in extreme scenarios, the catastrophic melting of internal transformer components. History provides stark reminders of this power. In September of 1859 AD, the British astronomer Richard Carrington witnessed a titanic solar flare on the Sun. Less than 18 hours later, the most powerful geomagnetic storm in recorded history struck Earth. Auroras were so blindingly bright across the Caribbean that gold miners in the Rocky Mountains woke up and began cooking breakfast at midnight, believing it was morning. Telegraph systems worldwide went haywire. Telegraph paper caught fire. Disconnected machines continued sending messages using only current induced from the air, and operators received severe electrical shocks. In March of 1989 AD, a severe solar storm struck Earth and induced massive currents into the Canadian power grid. In less than 2 minutes, the entire Hydro-Québec electrical network collapsed, plunging 6 million people into freezing darkness for over 9 hours. In October of 2003 AD, the famous Halloween storms forced commercial aircraft to divert away from polar routes, caused multiple satellite malfunctions, and triggered blackouts in parts of Sweden. In 2026, the stakes are exponentially higher because human civilization has become profoundly reliant on space-based technology. In low Earth orbit, thousands of commercial and government satellites orbit within the outermost fringes of Earth's atmosphere. When solar flares and CMEs heat the upper atmosphere, the thermosphere expands outward like a heated balloon. This sudden expansion dramatically increases atmospheric drag on satellites. During strong solar activity, satellites lose altitude rapidly and experience severe orbital decay. Operators must expend precious onboard fuel to boost orbits and prevent collisions or uncontrolled re-entry. In addition, high-energy particles penetrating satellite shielding can cause single-event upsets, flipping digital bits in computer memory and corrupting flight systems. Simultaneously, the turbulence in the ionosphere creates a phenomenon known as ionospheric scintillation, scattering and bending radio waves. This disrupts global positioning system signals, degrading GPS accuracy or causing complete signal loss. In our modern world, GPS is not just used for vehicle navigation, it provides the ultra-precise nanosecond timestamping required for international banking transactions, automated electrical grid synchronization, maritime shipping, cellular network towers, and aviation autopilot systems. Faced with these challenges, how does humanity prepare during this 2026 peak? Over the past 2 decades, space weather forecasting and infrastructure protection have evolved into a vital pillar of global security. Today, an international armada of advanced spacecraft keeps constant vigil over the Sun. Observatories like NASA's Solar Dynamics Observatory and the SOHO mission capture real-time, high-resolution imagery of the Sun in multiple wavelengths, identifying active sunspot regions before they erupt. Spacecraft positioned at the first Lagrange point, nearly 1 million miles upstream toward the Sun, such as the DSCOVR satellite, provide critical advance warnings of approaching CMEs, measuring their speed and magnetic orientation moments before impact. Groundbreaking missions like the Parker Solar Probe and Solar Orbiter are flying closer to the Sun than ever before, dipping into the corona to unravel the fundamental physics of the solar wind at its birthplace. On the ground, power grid operators utilize these early warnings to implement defense protocols. When a severe space weather alert is issued, utilities can reduce power transfers across long transmission lines, disconnect vulnerable transformers, activate capacitor banks to absorb excess current, and bring backup generation online to maintain grid stability. Pipeline operators adjust protection systems to prevent corrosion, and aviation authorities reroute polar flights to lower latitudes where communication and radiation shielding remain reliable. The 2026 solar maximum is a profound reminder of our place in the cosmos. It is not an apocalyptic threat or an unnatural anomaly. It is the natural, healthy heartbeat of a 4.5 billion-year-old star. For millennia, our ancestors looked up at the dancing auroras with wonder and awe. protected beneath Earth's atmospheric cocoon. Today, as we extend our electrical grids across continents and our digital eyes into orbit, the sun's magnetic pulse challenges us to become wiser and more resilient stewards of our technology. By decoding the intricate physics of the solar cycle, we learn not only how to protect the interconnected world we have built, but also how to appreciate the magnificent cosmic dance that sustains all life on Earth.